Hi guys, and welcome to this virtual lecture course in Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and this is the first lecture in this course. I would recommend that you watch these lectures of this course in sequence, starting with this one. It's a good place to start, and you can do that using the YouTube playlist for this course. So in this lecture, I basically want to introduce some of the ideas and concepts behind quantum condensed matter physics. First of all, we'll unpack the reasons why quantum is different and why it's interesting. Small is different. We'll also see that more is different in condensed matter physics. When we bring together a large number of particles, we see that we get collective and emergent behavior that is different from the behavior of individual particles. When we talk about the large number of interacting particles being quantum particles, we'll see that we get a rich range of phenomena which describes the diversity of the natural world. This is an interesting subject which is a useful subject, it's a vast subject, and it really describes the world around us, starting from the microscopic fundamental theory of quantum mechanics. After this somewhat philosophical introduction, we'll get down to business, and in the second part of today's lecture, I'll be talking about some of the basic ideas of quantum theory which we're going to need in this course. For most of this course, we'll see that we can build things up from scratch, and there isn't actually that much knowledge that's presupposed, but I'll just do a bit of a recap in today's lecture of some of the things that we do need to know. In particular, the idea of indistinguishability of quantum particles. And this gives rise to the idea of exchange statistics. We have fermions and we have bosons. In particular, electrons are fermions. I'll talk briefly about how we can have more exotic kind of particles arising in condensed matter physics as quasi-particles rather than fundamental particles, and that we might be able to do things called braiding of these particles to exploit their exotic exchange statistics. We'll see how that can actually be useful as a resource for quantum computation. I'll briefly touch upon that in this lecture. It'll be unpacked further in the future lectures of this course. One of the most important consequences, however, of the fermionic exchange statistics is the Pauli exclusion principle, and this is something that we're going to need to rely on quite heavily in this course. We can actually already see from the Pauli exclusion principle why it is that metals and insulators have such vastly different properties, and I'll talk about this towards the end of this lecture. So let's get down to work. In this lecture course, we'll be studying quantum condensed matter physics. So before we begin, let me make some remarks about what's special about quantum and what's special about condensed matter, so that we can get a sense of why quantum condensed matter systems are so fascinating, so diverse, and so complex. Let's start by unpacking what's so different about the quantum world. Well, we know that small is different. When we get down onto the nanoscale of atoms and electrons and so on, we see that the universe looks very different indeed. We have wave-particle duality, superposition, entanglement, quantum interference, all of these things. The field theory description of quantum mechanics and Feynman's path integral formulation tell us that any and all possible trajectories of a system can, and in fact do, play out simultaneously, with the observed result being the consequence of quantum interference between these trajectories. This allows us to understand the origins of the principle of least action, and hence make the connection between quantum and classical mechanics. On the mathematical level, we have non-commuting operators, which is a consequence of the finite value of Planck's constant h bar. We also have a quantum mechanical wave function describing the state of a system, with the classical notion of a particle position now being replaced in quantum mechanics by a probabilistic particle density, in turn related to the quantum wave function. The wave function is of course an eigenstate of the corresponding Hamiltonian operator and satisfies the Schrödinger equation. All of this gives rise to exotic new behaviour on the nanoscale. When we're looking at the properties of individual atoms or electrons, we see this very clearly, for example in the double slit experiment. Indeed, in the context of the modern field of nanotechnology, we see these quantum phenomena come into play in a very useful way. For example, in nanoelectronics, we see device properties that are very unlike their classical counterparts and actually give us a quantum advantage, ultimately we hope, of course, to utilise this for quantum computation, and we'll touch upon that a little bit in this course. So, small is different. We do expect things to be different on the nanoscale. However, all the matter in the universe, even on the macroscopic scale, is made up of constituents, atoms, electrons, and so on and so forth, which are governed according to the laws of quantum mechanics. If we take an ordinary object in the macroscopic world, which we take to be behaving classically, and we zoom in, we will see, of course, that it's made up of quantum particles behaving according to the laws of quantum mechanics. Somehow or other, when we combine a vast number of these quantum particles in the thermodynamic limit, 10 to the 23 particles or so, we see that this conspires to give us the physics and the behaviour that we expect in the classical world. How does that happen? Indeed, we know that most of the stuff we encounter on Earth is just made up of protons, neutrons, and electrons. The atoms are either assembled into molecular objects or into more extended materials. But from these very simple quantum building blocks, we're able to construct the fascinatingly diverse range of physical phenomena that we see in the natural world. We have all these different kinds of materials, we have metals and insulators, they can be different colours, they can be shiny, they can have different electrical properties, all of this stuff just coming from the same simple building blocks governed by the same quantum mechanical laws. So although we would usually consider quantum mechanics to apply on the nanoscale, of course all of the everyday objects that we encounter are made from these quantum constituents. And in some cases, when we zoom out, we get entirely classical behaviour. But not always. Consider, for example, superconductors and superfluids. These are objects on the macroscopic scale which are inherently quantum mechanical. There's no classical description of a superconductor. And there are other kinds of matter as well. For example, the recently discovered topological quantum matter. These have rather different kind of properties, which we'll be discussing towards the end of this course. So even on the macroscopic scale, quantum mechanics can still play an important role. In the context of nanotechnology, where we have quantum devices and quantum nanoelectronics, we see that even though we have a macroscopic circuit with a regular battery and so on, if we have a nanoscopic quantum component in that circuit, then the properties of the nanoelectronic device will again be entirely quantum mechanical. An extreme limit of this is so-called molecular electronics, where a single molecule can be placed as a functional component in an electronic circuit. All of this points to the fact that quantum mechanics is fundamental to our understanding of the natural world. And while small is in fact different, everything is made up of small stuff in the end. As for condensed matter, this can be characterized by the phrase more is different, a phrase popularized by the famous physicist Phil Anderson. I touched upon some of this already. The basic idea is that when we bring together a large number of interacting particles, we see very different kind of behavior. We see collective or emergent phenomena. When we have many interacting particles, the behavior is very different from that of a single particle or from many non-interacting particles. We see this already in the classical world, a stark example of which would be a memoration of starlings. Each starling follows a simple rule: simply head in the direction where most other starlings are. And when lots of starlings all follow the same rule, we get these fascinating patterns in the sky. This is a collective or emergent behavior arising from a very simple rule. We see other classical examples of collective or emergent phenomena in crowd dynamics, or for example the behavior of traffic on a crowded motorway. What we'll be interested in this course, will be the collective and emergent behavior of many quantum particles. We'll see that this is very much more rich and interesting. For example, when we bring together a lot of interacting quantum particles, we can get metals, or insulators, or superfluids, or superconductors, or we can get topological insulators, we can get quantum spin liquids, we can get all of this very interesting and exotic stuff, displaying a rich range of physical phenomena. In this course, we want to develop a conceptual framework for understanding this kind of physics. How can we model these systems? and how can we solve those models? Why is the many-body problem hard, and what ingenious strategies can we come up with to solve the unsolvable? To drill down a little bit more into the philosophy behind the subject, I want to discuss a very, very interesting article called More is Different by the famous physicist Phil Anderson. Phil Anderson, pictured here, was the Nobel laureate in 1977 in physics and has really contributed vastly across different areas of physics, as well as really being the father of modern quantum condensed matter physics. In this article, published in Science in the year 1972, Anderson really sets out his vision and his idea of the subject. It's actually more like an opinion piece than a scientific article, so I'd advise you get your hands on it and give it a read, because it's a really fascinating and interesting article. I will now try to summarise or paraphrase the basic argument for you. Anderson says that among certain scientists, and indeed people outside of science, there is a certain idea of reductionism. The idea that the workings of our minds and our bodies, and all of the animate and inanimate matter of which we have any detailed knowledge, are assumed to be controlled by the same fundamental laws, which, except in some very unusual and extreme conditions, we know pretty well. Basically, it's quantum mechanics, relativity, and so on. So reductionism is the idea that you can learn more about something by asking, what is it made of? Break it down into something smaller and smaller. The reductionist philosophy leads you to conclude that the only scientists studying anything fundamental are those ones working on the fundamental laws. In practice, this means some astrophysicists, elementary particle physicists, and a bunch of logicians and mathematicians. But the problem with this philosophy is that reductionism does not imply constructivism. The ability to reduce everything to fundamental simple laws does not imply the ability to start from those laws and reconstruct the universe. Why is that? The answer is scale and complexity, and this is known as the many-body problem. Bob Laughlin, another Nobel Prize winner in theoretical physics from this time 1998, says, for many particle systems, nothing can be calculated exactly from the microscopic equations. Macroscopic systems are characterized by broken symmetry. The symmetry present in the microscopic equations is not present in the macroscopic system due to phase transitions. As a result, these macroscopic many-particle systems are described in terms of their own terminology. They have emergent properties that do not depend on the microscopic details, or at least not many microscopic details. This also gives rise to the notion of universality. Now, the kind of broken symmetry that Laughlin is referring to here is, for example, the broken translational or rotational symmetry of free space, which is homogeneous and isotropic, when a solid forms with a particular crystal structure, or magnetic ordering sets in a magnetic material below, for example, the Néel temperature. So reductionism would lead you down the rabbit hole if, for example, you wanted to describe a glass of water. The water is made of molecules. The molecules are made of atoms. The atoms are made of protons and neutrons and electrons. The protons and neutrons are made of quarks. These are made of strings, and down and down and down. But what have we learned? We don't get anywhere near answering the kind of questions such as, why is water wet? Why is it transparent? When does it freeze? We didn't really learn anything useful at all. So reductionism completely misses the forest for the trees. More often than not, if you want to understand the physical properties of something, you have to ask about the big picture. How do the pieces fit together to make the whole? The more the elementary particle physicist tells you about the nature of the fundamental laws, the less relevance they seem to have to the very real problems of science, much less to society. The behaviour of large and complex aggregates of elementary particles, it turns out, is not to be understood just in terms of the simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear. The understanding of the new behaviour requires research, which Anderson argued is as fundamental in its nature as any other. At each new stage of scale and complexity, entirely new laws, concepts, and generalizations are necessary, requiring inspiration and creativity to just as great an extent as in the previous one. Even at the rather high level of quantum condensed matter physics, which may be regarded as being closer to the fundamental underpinnings than most, we see how totally different laws and physics emerge. The elementary particle physicists might tell you of the symmetry of space, isotropy, homogeneity, and so on, even a grander supersymmetry. But in the most elementary material, for example rock salt, sodium chloride, this symmetry is broken. We have a crystal lattice with a lower symmetry. How does this happen? The quantum state is apparently a superposition, like Schrödinger's cat, of all the possible symmetry states. But for macroscopic systems, they just get stuck in one of these symmetry states. It takes a huge amount of energy to transform a many-particle system from one of these to another. Or put another way, the timescale for quantum tunneling between different symmetry states is very, very long compared with, say, the age of the universe. So in the end, the laws we are dealing with, in effect, are not the microscopic ones at all, but emergent new laws which we need to discover and study from scratch. So why study condensed matter physics? Well, the first reason is that it is a vast, vast subject. As the Oxford physicist Steve Simon says, it's basically 1/3 of the whole of physics. Consider the following thought experiment. If you go around the world and ask every single physicist, are you a condensed matter physicist? 1 in 3 of them would say yes. It's the largest subfield of physics. Largest by far, it's very broad and it's very diverse. It includes many different topics within it. And in this lecture course, we'll touch on just a few of those. There have been 112 Nobel Prizes awarded in physics in the history of the prize, and well over half of these have been for advances in condensed matter physics. John Bardeen, for example, won 2 of them for the transistor and the superconductor. These are both advances in condensed matter physics. As an example of how big and broad and diverse condensed matter physics is, you can just have a look at the March meeting of the American Physical Society as an example. This is a conference every year in the US, and roughly 10,000 physicists attend, all studying condensed matter physics. It is a vast conference, and the range of topics on offer is really quite staggering. The next reason is that it really describes the world that we live in. Condensed matter physics is the study of the stuff in the world around us. It is the study of matter, and it is the study of the different types of matter that can exist and the properties of that matter. From metals to magnets, from graphene to superconductors, from amorphous glasses to fractionalized spin liquids, there's an amazing array of different materials out there. And it's a huge intellectual challenge to understand these. Why, for example, is it that a lump of copper has 10 to the 20 times lower electrical resistance than a diamond, despite the fact that they are both crystalline solids made up of protons, neutrons, and electrons? Condensed matter physics is also useful. It's by far and away the most technologically important field of physics. We've come to an incredible control over the stuff of the world through this study, for example, electronics, material science, and so on. Condensed matter physics has great practical importance. For example, the superconductor. It is used in MRI machines in medicine. It's used on magnetic levitation trains. It's used in energy storage, transmission, power generation. This is just one material, and without a detailed understanding of it that physics provides, we wouldn't be able to have any of these technological advances that follow from this material. Yet, high-temperature superconductors are still an active field of research. There are many open questions surrounding this topic, and important discoveries are yet to be made. Condensed matter physics is also fundamental, and it's deep. It tells us about the very nature of the material in our world. The ideas that have been developed to explain condensed matter physics are just as deep as in any other area of physics. And very often, those concepts have been developed in condensed matter physics and then been taken over to some other areas of physics. A good example of this is the Higgs boson. The basic idea there was borrowed from condensed matter physics. It was actually Phil Anderson, who I mentioned earlier, who pointed out that when metals become superconductors, the mechanism for this is somewhat similar to what we now know as the Higgs mechanism. And finally, the most important reason to study condensed matter physics is that it's fun. It's one of the most complex and interesting subjects in all of science, and coming to master this subject and understanding something deep about our world is certainly rewarding. Right, so let's get down to work. The microscopic laws governing all condensed matter systems is, of course, quantum mechanics. The most complete description of nature available to us is, after all, quantum theory, and ultimately, in some sense, it must explain all of the complexity in the world, all of the different states of matter that I mentioned, from solids, magnets, superconductors, and so on. We can write down the Schrödinger equation, h psi is equal to e psi, for a given wave function labelled by this label alpha here. This wave function psi sub alpha is something that depends on the coordinates of all of the particles, r1, r2, r3, and so on, all the way up to Rn for a system of n particles. E sub alpha here is then the energy of that eigenstate. The Schrödinger equation is therefore an eigenvector equation with the wave function psi sub alpha being the eigenvector of the Hamiltonian h. Amazingly, we actually know what the Hamiltonian is. It comprises a kinetic energy term and a potential energy term, and we know the form of both of these. This is not like in high-energy particle physics, for example, where you don't really know the Hamiltonian, you have to guess it. Here, we really do know. And indeed, I can write it down on one line. Here it is. We have the sum over particles j from 1 to n, where n is the total number of particles, and we have this kinetic energy term here involving, as it does, this second spatial derivative. And then we have a potential energy term, which involves pairwise interactions between particles j and k. We also know exactly the form of this potential here. We know, for example, that electrons interact via the Coulomb interaction, and we know what the Coulomb law is. And here it is in closed form. This equation, as I've written it down, basically captures almost all of the physical phenomena that we'll be interested in. You could write down corrections to this equation, but those corrections are themselves basically known, and it in essence doesn't really increase the complexity of the problem. So, even though we know the fundamental laws of nature, and here it is, we cannot predict from first principles the exact physics of many interacting quantum particles. I could do a good job of predicting how a single particle moves in an applied potential, and I can equally well predict the motion of two interacting particles by separating the centre of mass and interparticle coordinates, for example. But there are actually only a few special cases involving even three particles that we can solve exactly, even in the classical world, let alone the quantum world. But the phenomena we commonly observed in the natural world obviously involves not 2 or 3 particles, but 10 to the 23 interacting particles. N is equal to 10 to the 23 in our equation here for the Hamiltonian. So, how would we solve such an equation? Well, the quantum mechanics we learnt so far was basically for 1 and 2 particles, and now we have 10 to the 23 particles, so there's a bit of a disconnect there. In fact, there is no general analytic solution for the motion of all of these particles. No exact solution to the Schrödinger equation exists, not even in principle. But even if such a solution did exist, it would be useless. What could we possibly do with all of that information? We could not possibly observe the motion of each of the 10 to the 23 particles. And anyway, we're not really interested in that. The kind of things we want to know are different in condensed matter physics. The kind of things we observe are macroscopic variables, such as particle density, energy density, magnetization, conductivity, stiffness, colour, thermal and optical properties, these kind of things. We can measure these things, and we can also measure their fluctuations and their responses to external fields. It's these kind of quantities that characterize and distinguish the many different phases of matter. Liquids flow, solids are rigid, some are transparent, some are shiny, there are metals and insulators, superconductors and superfluids, and so on and so forth. Nature provides us with an almost unlimited variety of interesting and complex interacting many-body condensed matter systems. Condensed matter physics provides a framework for describing them and understanding them. Quantum condensed matter studies systems from the perspective of quantum mechanics as the microscopic theory. It allows us to study more interesting and complex systems where exotic quantum effects emerge on the macro scale in bulk systems. First, before we start studying quantum systems with many particles, we need to understand the fundamental properties of identical particles themselves, and how things are different in the quantum world than in the classical world. For a single particle, there is no problem. We can write down and solve the Schrödinger equation. But even for two particles, we need to be more careful. What do we mean when we say that two particles are identical? In quantum mechanics, we have a much stronger definition of identical particles than in classical mechanics. This is important because it puts restrictions on the kinds of states that can be eigenstates of a Hamiltonian describing a quantum system involving several particles. That is, it puts restrictions on the form of the wave functions that solve the Schrödinger equation. We need to be careful with these considerations in quantum condensed matter physics because we are dealing with systems with many identical quantum particles. Consider a system of several identical particles. In classical mechanics, we're happy to say that they are essentially identical. Consider this illustration of a pool table. We have a bunch of balls on here, and these balls all have the same mass, they have the same shape, they have the same radius and the same texture, and so on. But we can make them distinguishable by colouring the balls. For the sake of this illustration, I got 1 white ball, 1 black ball, 3 red, 3 blue, and 3 green. The mechanical properties of these balls won't be changed simply by changing the colour, and so we would say that they're essentially identical, but we're still able to distinguish the different balls through the colour. Let's say this is the initial configuration, and after we strike the cue ball, we have a final configuration. In the final configuration, the balls are scattered across the table, but because of their colourings, we can see which ball went where. The fact that we've coloured the balls doesn't affect the classical mechanics of the problem. This allows us to say which ball in some initial configuration ends up where in the final configuration. If we were to take the collision between two balls, for example, we would see that we start off with this black ball, let's say ball number 1, and we can trace its trajectory throughout the path. We start off with 1, it continues to be 1, and it ends up being 1. On the other hand, the red ball, let's label that 2, we can also trace its trajectory. It remains particle number 2, or ball number 2, throughout its trajectory. The fact that we know which ball in the initial configuration ends up where in the final configuration is a property of classical mechanics. This kind of statement about how one specific particle goes from one place to another is forbidden in quantum mechanics. In quantum mechanics, we can have the collision of two particles, but we cannot say which particle ends up where. The identification of the particles like this would require a continuous observation in time, and this destroys the coherent quantum state. That's because observation in quantum mechanics is projective. A measurement of the quantum state collapses the wave function to a classical state. Therefore, to identify what happens throughout this collision, we'd need to constantly observe it. If we do not observe it, then the system can remain in a quantum coherent state. But then, the identical particles are truly identical, and we don't know which one went where. Why is this, and how do we know that this is true in quantum mechanics? Well, consider the famous double slit experiment. So here we have some gun which fires out some electrons, let's say, and it's firing out those electrons one at a time. And the electrons can pass through one or other of these two slits in this screen here, and then they arrive on the back wall here, where we have a detector that counts them. So over time, we see that the detector will register when the electron hits the back plate here at a particular position, and then we can make a histogram probability distribution of where the particles are arriving. Famously, we see a quantum interference pattern for electrons arriving at the back plate, even though these electrons only arrive at the back plate one at a time. One can explain this pattern by considering the interference between trajectories of electrons passing through one or other of the slits. However, that does imply that the electrons are passing through both slits simultaneously. This all arises because we have multiple equivalent but unobserved quantum trajectories. The unobservability of these quantum trajectories is the key to the whole thing. and it is also at the heart of the indistinguishability of particles in quantum mechanics. We can't observe the particles throughout their motion to distinguish between them. If we were to observe the quantum particles to distinguish them, then it would destroy the quantum effects. This is seen very clearly in the double slit experiment. If I sit behind the screen and observe instantaneously which electron passes through which slit. Then I obtain two probability distributions, one for electrons arriving at the back screen that passed through this top slit, that's the red one, and a different probability distribution for electrons arriving at the back screen which passed through the bottom slit. If I can distinguish them, then this nice quantum interference pattern in the upper panel here disappears. So that demonstrates that for quantum coherence, we need these unobserved trajectories. And if we're not observing, then we can't distinguish. And it's just the same in a many-particle quantum mechanical system. If we try to find out which particle in the initial configuration winds up where in the final configuration, then we're destroying the very quantum effects that we're interested in. So the punchline of all of that is that we have to take quantum indistinguishability very seriously indeed. It's a much more stringent condition than the effective indistinguishability of particles in the classical world. Let me now remind you how this notion of quantum indistinguishability is encoded on the mathematical level of quantum theory. As you probably know, what all of this means on the level of the quantum mechanical wave function is that we can swap the coordinates of the particles around without changing the physical properties. And remember, the wave function itself is not an observable. An n-particle system is described by an n-particle wave function, denoted psi, which has arguments which are the coordinates of all of the n particles, r1 vector, r2, r3, and so on, all the way up to Rn, the position of particle number n. Of course, the probability density is an observable. According to the Born interpretation, if we take the square modulus of the wave function, this gives us the probability density of finding a particle in that particular region of space. So let's consider the specific probability density for a given wave function, psi, focusing here on particles I and j. Because of the quantum indistinguishability of particles I and j, we can swap their coordinate labels, and we note that physical properties must be unchanged. In particular, given that the probability density is an observable, it tells us that these two wave functions here, one with Ri and Rj, and the other one with these labels swapped around, the square modulus of these wave functions must be equal. So this tells us that permuting a pair of particle labels induces at most a quantum phase. What this means is that we can relate the wave function with labels Ri and Rj to the wave function with labels Rj and Ri simply by a complex number of modulus 1. We write that as e to the I chi in terms of this phase chi. This is a convenient choice because when we take the square modulus of e to the I chi, we get 1 independent of the angle chi, and therefore the square modulus of these two wave functions will be equal. But what happens if we swap the labels twice? Well, we must get back to where we started. We swap the labels I and j to j and I, and then swap them again back to I and j. By using this formula, we would then accumulate this factor of e to the I chi twice. That means that we have a wave function which is equal to itself times e to the I chi squared. This then tells us that e to the I chi squared must be equal to 1, and therefore when we take the square root, we learn that e to the I chi can either be plus or minus 1, and those are the only two options. The phase must square to 1. This phase encodes the so-called exchange statistics. There are two types of particles that are found in nature, one in which the phase e to the I chi is equal to plus 1, and we call those things bosons, and one where e to the I chi is equal to minus 1, and we call those fermions. An electron, for example, is a fermion, and we'll be discussing the consequences of these exchange statistics a lot in this lecture course. There is, in fact, a deeper understanding of how this difference comes about through relativistic quantum field theory, but I don't want to get into that in this course. Let's just take it as read here as an observational fact about nature, and note that electrons, which are spin-half particles, are fermions, meaning that they are antisymmetric under exchange of particles. these exchange statistics really do make a measurable difference in physical properties. A classic and very stark example of this is to compare the two isotopes of helium. Helium-4 has 2 electrons and 2 protons, of course, but also 2 neutrons, whereas helium-3 has 2 electrons and 2 protons, but only 1 neutron. Helium-4 therefore has an integer spin in total and is a boson, whereas helium-3 has a half-integer spin and is therefore a fermion. One can cool helium down, we believe, to absolute zero at ordinary pressures, and the helium will remain a liquid. That is, the particles are free to move around and exchange positions. At low temperature, where quantum effects become important, helium-4 becomes a superfluid below 2 Kelvin. This has been observed. It flows without viscosity. If stirred, it will form a vortex which will rotate forever without resistance or dissipative loss. This is a Bose-Einstein condensate, and we will discuss this example later in the course. It is an exotic state of quantum matter arising because the bosons comprising the liquid helium can condense into a single quantum state in macroscopic quantities. On the other hand, helium-3, being fermionic, cannot do this directly due to the Pauli exclusion principle, which we'll talk about in a moment. Pairs of helium-3 atoms can, however, combine and condense in a manner similar to Cooper pair formation in superconductors, and a different kind of superfluid quantum state forms, at temperatures 1,000 times lower than for helium-4. So these differences between fermions and bosons really do play out in physical properties of these systems. Now I'd like to briefly touch upon the connection between the exchange statistics and that of the emerging field of quantum computation. Let's consider n indistinguishable quantum particles. Particle exchange, of course, leaves the physical properties unchanged. This actually implies that there is a huge redundancy in the description of the wave function. The idea in quantum computation is to utilize this as a resource. This is done through the concept of braiding. Let's draw a graph of 2 particles and their positions as a function of time. In the initial configuration, let's say that we have particle 1 on the left and particle 2 on the right. Let's say some time later we arrive at our final configuration, in which we still have the particles in the same positions. Let's now imagine that we can chart the world lines for these particles. By the world line, I simply mean the position as a function of time in this kind of space-time diagram. Let's say that particle number 1 moves around in some particular trajectory and then ends up again on the left. This is particle 1. Meanwhile, particle 2 takes some other trajectory and ends up in its final position, number 2. Now bear in mind, of course, that in a real quantum experiment we want to maintain the quantum coherence, so we wouldn't be observing these trajectories during this intervening time. But what we can do is to contrast this scenario to a different one, in which particle 1, initially on the left, crosses over and ends up being on the right-hand side, while particle 2 obviously crosses and ends up on the left-hand side. So if we were able to really label these states, then we would see that they have been exchanged in the scenario on the right-hand side, but not exchanged in the scenario on the left-hand side. The many-particle quantum wave function describing this system would therefore be different on the left than on the right. We have this additional phase factor, which, if they're fermions, would give us an extra minus sign for the scenario on the right-hand side relative to that on the left-hand side. The particles end up in the same positions at the same time, however, they've been exchanged in the meantime. Because we have particles in the same positions in the initial condition and in the final condition, these states of the system have the same energy, but their wave functions are related by this phase. Now let's consider a slightly more complicated case. Now let's consider the situation with 3 particles. Again, we have 3 particles occupying exactly the same positions in the initial state and the final state. However, the individual world lines of these 3 particles can be different. Consider now the following scenarios. On the left-hand side, Let's say that particle 1 and 2 initially swap positions, and then particle 2 swaps over and goes onto the right-hand side, whereas particle 1 remains on the left-hand side. Meanwhile, particle 3 simply exchanges with particle 2 and ends up in the middle. Now let's consider a different sequence of world lines that actually gives us the same final configuration. On the right-hand side, we see that particle 1 just coasts towards its final position and remains on the far left position. Particles 2 and 3 simply exchange positions. So you see, in these two different scenarios, particles 1, 2 and 3 end up with a different configuration. We see they end up in the order 1, 3, 2 on the left, and also 1, 3, 2 on the right-hand side. Because the start and end points are the same, there is therefore no statistical phase difference for fermions and bosons. But, as you see, the order of operations is different. In fact, we can make a whole group out of the different combinations of events in these world lines, and these form the so-called braid group. Tying these kind of knots in the world lines is referred to as braiding. Now, there are exotic particles with different phases, not just plus and minus 1 for fermions and bosons, but some kind of intermediate phase, and we call these not fermions or bosons, but anyons. These anyons have different exchange statistics, and in fact different braids give different states, and this is actually what's needed for quantum computation. Imagine that we have a bunch of different indistinguishable anyons. The ground state manifold of this system has a high degeneracy because we can imagine permuting all of these different pairs of particles to obtain a state of the same energy. However, for anyonic systems, the world line histories of these particles matters, and in fact, as we braid the particles around each other, we encode information. This is quantum information, and it's something that can be manipulated and stored by braiding the particles around each other. Even though the start and end configurations are the same, we can actually encode quantum information by this braiding operation. It is actually the anyonic exchange statistics that's required for this kind of powerful quantum computation. However, anyons are not fundamental particles in nature. As we saw, we only have fermions and bosons in nature. So how on earth can this possibly work? Well, the idea is that these can be emergent quasi-particles in condensed matter physics. We'll talk about some examples of these emergent quasi-particles later on in the course, for example Majorana fermions, which are their own antiparticle. Again, these are objects that do not exist as fundamental particles in nature, but can emerge as collective behaviour in many particle systems. So I won't say much more about quantum computation at this stage. I will just emphasise that the role of exchange statistics is crucial, and the kind of exchange statistics we need for powerful quantum computation actually can only come from complex condensed matter systems. A very important consequence of the fermionic exchange statistics is the Pauli exclusion principle. This is something that results from the antisymmetry of the fermionic wave function. Naively, we might have thought that if we have two independent fermions, then we might expect a factorized form of the two-particle wave function. Here, psi, which is a function of the particle coordinates r1 and r2, is the two-particle wave function, whereas phi a and phi b are different quantum orbitals that can hold a single fermionic particle. We might have expected such a factorized form for independent fermions because they do not interact. The presence of one does not affect the presence of the other. Now, in probability theory, if two events are independent, then that means that their probabilities factorize. So given the Born interpretation of the wave function, we might have expected in quantum mechanics that the wave function of a system of two independent particles is a product state. That is, it factorizes into the product of single particle wave functions. After all, the probability density is given by the square modulus of the complex wave function, and the square modulus of a product is equal to the product of the square moduluses. This all sounds sensible, but it's not correct, because it is not consistent with the fermionic exchange statistics, whereby we get a relative minus sign when we swap the particles around. Therefore, to obtain the proper two-particle wave function, we need to properly symmetrize it. The fermionic antisymmetry actually requires a wave function of this form. We can see here that if I swap the R1 and R2 labels, then the first term turns into the second term, and the second term turns into the first term, and overall, we get a relative minus sign. An important consequence of this is what happens if we try to put two fermions in the same state. This is equivalent to saying that phi A of R is equal to phi B of R. In that case, we would naively conclude that these two terms in this expression for the two-particle wave function psi cancel each other, and we'd obtain psi of R is equal to 0. However, that's actually also not correct, because the wave function must be something that normalizes to 1 when you integrate over all space, so the wave function here can't actually be equal to 0. All we conclude from this is that no such wave function exists. We cannot put two electrons in the same quantum orbital. All of this is probably very well known to most of you watching, and you might be wondering what all of this has to do with condensed matter or solid-state physics, which involves not two particles, but 10 to the 23 particles. Well, the Pauli exclusion principle tells us that at most we can put one electron in each quantum state. This actually has enormous significance for the physical properties of condensed matter systems. To see this, let's look at a simple example. Let's return to one of the distinctions that I made at the very beginning of this lecture, the difference between metals and insulators. How can we understand the huge difference in physical properties between, for example, copper and diamond? Let's say that you bring together a large number of copper atoms and investigate the electrical resistivity. Or we could bring together a large number of carbon atoms in the form of a diamond and look at the resistivity of that material. Copper has a resistivity of roughly 1 times 10 to the minus 8 ohm meters, while diamond has a resistivity of 1 times 10 to the 12 ohm meters. This is an incredible difference. It's a factor of 10 to the 20 between the resistivities here, 20 orders of magnitude. How does this come about, and what's it got to do with the Pauli principle? The difference between metals and insulators is one of the basic questions in condensed matter physics. First of all, we'll need to consider the electron energy bands in solids. This is related to the field of band structure, and we'll be discussing that more later on in the course. First of all, let's consider a single atom of either copper or diamond, let's say. For simplicity, let's imagine that this atom has just two quantum orbitals, and imagine that they have different energies, which I've denoted here by these two lines in this energy level diagram. Now imagine that we had two atoms, but infinitely far apart. What would happen is that both of those atoms would have the same pair of energy levels, and each of these levels would therefore be doubly degenerate. There would be two orbitals at this energy and two orbitals at this energy. However, as I bring these atoms together, the electrons will be able to tunnel quantum mechanically from one atom to another, from one orbital to another. This induces, as we'll see later on in the course, an energy level splitting between these hybridizing orbitals. We still see this overall gap between these two levels, but now the degeneracy of each of those levels is lifted. The closer we bring these atoms together, the stronger the hybridization between the corresponding orbitals, and the greater this energy level splitting here. In a normal crystal lattice, this splitting here between these levels will be much smaller than this separation between the original levels of a single atom. Now let's step up to many atoms arranged in a crystal lattice. We might then expect to see something like this, with a whole bunch of levels in this upper band and this whole bunch of levels here in this lower band. Indeed, as we go to the thermodynamic limit of a very large number of atoms arranged in an extended crystal lattice structure, we would expect to see a continuum of states forming these different bands. Within these bands, there are lots of states, and therefore electrons can take any energy inside this range. However, there are no states in this energy gap here. So what do we do with this information, and how can we understand now the resistivity of copper and diamond? And for that matter, what has this got to do with the Pauli principle? Well, the Pauli principle comes into play when we want to accommodate all of the electrons in the solid into these energy bands. How do we do that? In a typical solid, we have a continuum of states forming bands. So let's just represent the continuum states in each of these bands in the solid in the thermodynamic limit of a large number of particles, just as these boxes. This represents one band, this represents another band. Now, we want to put electrons into these energy bands. At low temperatures, and in practice this means even at room temperature, we want to arrange the electrons in the lowest energy configuration. But when we're finding this configuration, we must take into account the Pauli exclusion principle. Because electrons are fermions, we can only put one electron in each individual level of the band. And so we just fill up the boxes, starting from the bottom, and find the lowest energy states. There are basically two distinct ways this can play out. On the one hand, we'll get a metal, and on the other, an insulator. In the case of a metal, we fill up the lowest band with the electrons that we have in the solid, and we reach a certain point, which is the highest filled level, or if you like, the lowest unfilled level. This is called the Fermi level, or the Fermi energy. In a metal, the Fermi level is inside one of the bands. So in a metal, we have partially filled bands. Now, if electrons were actually bosons, then all of these electrons could occupy the lowest quantum state, because we wouldn't have the Pauli exclusion principle. This means that we wouldn't have to fill up these boxes starting from the bottom and reaching up until the Fermi level. We could just put all of the electrons in the lowest quantum state. Now, of course, electrons are fermions, and we do have the Pauli exclusion principle. That means each quantum orbital in the solid can only be occupied by at most one electron. Therefore, we have to really start filling up these boxes from the bottom, and we reach a certain point, the Fermi level, which for a metal would still be inside one of the bands. So why is it a metal? Why does it conduct electricity? For a large system, the energy gap between the highest filled state in the solid and the lowest unfilled state is vanishingly small. This means that there are low energy ways of rearranging the electrons in the solid. In particular, if we apply an electric field, we can make a current flow easily by rearranging the electrons. By contrast, in an insulator, we have a completely filled band, and as you can see, the Fermi level is now sitting in the gap between these two bands. We just have a certain number of electrons in the solid, we have to accommodate them in the quantum orbitals that we have. We start filling from the ground state, and we eventually reach up and completely fill one of the bands. What this means, however, is that there is a large energy gap between the highest filled state, which is here, and the lowest unfilled state, which is here. The energy gap is basically the band gap, which is of order electron volts. An insulator therefore insulates because of this large energy gap. There are no low energy ways of rearranging the electrons in the solid. We'd have to apply an enormous electric field to promote an electron across this energy gap. Or likewise, we'd have to heat this material up to a very, very high temperature to have thermal excitation of the states in this upper band. So it is because of this band structure, and because we fill electrons in these bands according to the Pauli principle, that we see the absolutely enormous difference in resistivity between metals, where the Fermi energy is inside a band, and insulators, where the Fermi level is in the band gap. This is a rather simple but remarkable demonstration of quantum mechanics on the macroscopic scale. Here I just wanted to give you a flavour for some of this exciting physics, and in this course we'll be going into the detail of condensed matter systems and developing the rigorous theoretical framework in which to describe all of this physics.